Good afternoon, dear students. How are you all? Hello, everyone. Okay, so students, please report attendance, and we'll begin right away. All right. Shillong Center, please report attendance. All right, so in the last class, we were discussing the anatomy of flowering plants. So, in the anatomy part, what we have done so far includes the transverse sections of various plant organs. Good afternoon, Shillong. Yeah. Centers, please report your attendance. Okay. All right. So, in the last class, we had discussed a very important topic for your NEET examination, which is secondary growth. Okay. And leaf also. In leaf, only one question is asked normally. That is bulliform cells. Okay. In the last class, we had discussed about bulliform cells, large empty cells found in the upper leaf epidermis. They look like this, very large cells, and when they lose water, they suddenly shrink very quickly. So, when it loses water, it shrinks very quickly. Okay. So, it becomes very small, like this. So, this results in folding movement of the leaf. The leaf becomes like this, because these cells have suddenly shrunk together. So, the leaf will also shrink, it will fold. So, this is found in some particular monocot grasses, okay, and these are the bulliform cells. These are very important for your NEET examination, that is why I discussed this. Alright, and other than this, we discuss a number of stomata and stomata distribution pattern. Stomata distribution pattern is in monocots, both equal sides. Both equal sides have equal number of stomata. So, it is called isobilateral leaf. Okay. And dorsiventral leaf has more stomata on lower surface and less or no stomata on the upper surface. Okay. So, I hope you remember this. All right. So, carrying on, we had discussed a few things about the secondary growth. Secondary growth, that is a very, very important part. Secondary growth in dicot plants. In dicot plants or stem. Actually, we discussed dicot stem only. When we talk about dicot plants, it means secondary growth in dicot root as well. So, first of all, we will discuss secondary growth in dicot stem, then we will discuss the secondary growth in dicot root. And this we had discussed in the last class. Okay. So, you remember this part, we had discussed this up till this, that the medullary rays are formed, the secondary xylem is formed, all these things are formed. You remember this, everyone, right? So, the intrafascicular cambium plus interfascicular cambium is forming the cambium ring. Now, I have a question for you, for those who do not remember. The question is, what part of cambium ring is primary in origin? What part of cambium ring is primary in origin? It is comparatively quite easy, it should not be difficult. What part of the cambium ring is primary in origin? That is my question. Nobody? Look, I told you this. The cambium that is present in the vascular bundle, inside the vascular bundle, that is the primary origin. But combined with the parenchyma cells outside, which is the secondary meristem, we form the cambium ring, and that becomes the secondary meristem. So primary cambium, it is basically just the cambium present inside the vascular bundle, nothing more, nothing less. All right. But when you refer to the total overall secondary growth, we say that the whole cambium ring is considered secondary in origin, and the cambium is whether it is primary or secondary, it is combined called secondary meristem. So this is the secondary meristem, and this we had discussed. It forms secondary xylem, it forms primary, it forms a secondary phloem, and as well as that, it leaves some parenchyma cells behind. These parenchyma cells form rays called medullary rays. So everybody remembers this. After this, I had discussed that when the ring goes larger in size, there is a problem. The problem is phloem is synthesized less, xylem is synthesized more. So this leads to an issue that when we are synthesizing more xylem, less phloem, the outer bark of the plant, any tree that you see, it always shows some cracks. Everybody has seen some cracks, right? So the bark will show cracks. So how do we heal this bark? That is the question. Do you remember I told you the answer yesterday? I told you the answer yesterday that when you make less phloem, more xylem, the outer bark will crack, and the plant deals with this situation in another way. What is the substance that is synthesized by the plant to make up for the cracks? What is the substance? Yes. Do you remember? Everyone? No one? At least give me the name. Okay, what is the role of medullary ray? Medullary ray helps in lateral conduction of water. From outer to inner side, it helps in lateral conduction of water. Okay, these are living cells, and afterwards, very later afterwards, when the innermost cells are dead, these will also become dead. Very late. Okay, but normally they are living. So these are. My question to you is, xylem is synthesized more and phloem is synthesized less. What situation does this give rise to? What situation arises because of this problem? How does the plant deal with it? Do you remember? No one? Okay. I'll give you a quick revision, everyone. Look, listen carefully. In the initial stage, look at this diagram. In the initial stage, there is no cambium ring. There is no cambium ring. Only vascular bundles arranged in a ring-like fashion. Now, when the secondary growth has to happen, we need to complete the cambium ring. We need to complete the cambium ring. So one vascular bundle, cambium must join with the other vascular bundle. How? By making the cells between two vascular bundles convert by dedifferentiation into meristematic cells called cambium cells. If you want me to show you the exact diagram, it happens like this. Suppose this is one vascular bundle, this is another vascular bundle. Like this. This is one vascular bundle, this is another vascular bundle. This is another vascular bundle. Like this. Now, the cells in between, suppose I am showing them with the other color like pink color. These are parenchyma cells. These are parenchyma cells. Now, these parenchyma cells will convert by dedifferentiation because it is a parenchyma cell, so it has become differentiated to perform the function of a parenchyma cell. It will now convert into a cambium cell. Cambium cell. Okay. It will now convert itself into a cambium cell. So when it converts itself into a cambium cell, the cambium ring will become complete like this. Cambium ring will become complete. I'll show a larger vascular bundle like this. Like this. The cambium ring becomes complete. This is what is happening. This is what is happening. This is what is happening. So now, what is going to happen? These parenchyma cells will convert into the cambium cells. The remaining cells will not become, all the cells will not become cambium cells. Some cells will become. They only have to complete the ring. So now this cambium ring looks like this. You can see this in the next figure. This is the cambium ring. Let me show a marker. This is the cambium ring. My line is going thicker, but you understand what I am trying to tell you. This is the cambium ring. It will make new xylem vessels, new phloem tubes, sieve tubes and companion cells. Both will be made. Phloem will be pushed outwards, xylem will be pushed inwards, and the ring will keep on increasing in size. Ring will continuously keep on increasing in size year by year. So cambium moves outwards, xylem moves inwards, phloem moves outwards. This situation leads to a problem. Phloem is more, phloem is less, xylem is more. Phloem will undergo cracking. There will be cracks between phloem, and there will be cracks before phloem. There will be cracks in the cortex because of outward pressure. Xylem is made. Phloem is still being made. Cortex is not being made at all. So now cortex will be pushed outwards. Due to pressure, cortex will show cracking. What will cortex do? Cortex will develop a new kind of cambium. It is called cork cambium. Cork cambium makes new cells to fill the spaces in the cracks. These cells are called cork cells, the cells that Robert Hooke observed. First cell observed by Robert Hooke, or sorry, discovered by Robert Hooke. First cell seen by actually Leeuwenhoek. Okay, so these are the cork cells, empty hexagonal dead cells. These cork is a fatty substance, a moisturizing substance, you can say. I am just comparing it. It's not actually a moisturizer. It's a waterproof, airproof substance. So the plant produces it to protect itself from the pathogens. Okay, so this is the whole story. So now you can start writing this whole story. Please begin by let's start. The secondary growth in dicot stem takes place in 2 stages. Let's start writing. The secondary growth in dicot stem takes place in 2 stages. Or steps. The first step is formation of cambium ring. First step is formation of cambium ring. We must first complete the cambium ring. So everybody understands this. If you have even a slightest doubt, please feel free to tell me what doubt you have. Okay? Don't hesitate. Secondary growth takes place in 2 steps. Formation of cambium ring. This is happening first. Cambium ring is happening first. So what we will do to form the cambium ring? Yeah, you remember? Intra plus inter. I gave you the example. Intra-school quiz within the school. Inter-school quiz, inter-school competition, inter-school football competition. Between inter plus intra will together form the cambium ring. So you can say here, in dicot stems, the cells of cambium present between primary xylem and primary phloem and primary phloem is the intrafascicular cambium. Intrafascicular cambium. Okay, you can draw this. I will draw a vascular bundle for you. This is the shape of cambium cells. Very small, almost rectangular cells. Very small cells. These are the phloem cells. These are the phloem cells. Xylem cells, outer xylem vessels are larger, inner are smaller, like this. So this is the intrafascicular cambium. This cell here, you want me to label it in a different manner, like this. This cell. So if I want to choose a marker like this, these cells, these yellow colored cells, these are the intrafascicular cambium. Intrafascicular cambium. The word fasces has come from the European language term fasces, which actually refers to bundle. Okay, if you remember Hitler, Adolf Hitler's party was called the Nazi fascist party. They were called fascists. So that's the meaning of fascicle or fascium. So intrafascicular cambium. Okay. All right. Now what is the interfascicular cambium? So you will write now. Look, just between two vascular bundles, the cells which are present here, like this, these are called medullary rays. They help in lateral conduction of water. So these are the medullary ray cells, which are parenchymatous cells. So these are the medullary ray cells. This is the phloem. I am not drawing it again, you know that it is phloem. This is the xylem part. This is the xylem part, and these cells of medullary rays, medullary ray cells, these are parenchymatous cells. Okay, so we will now say the cells, the parenchyma cells of medullary rays adjoining the intrafascicular cambium become meristematic by dedifferentiation and convert into interfascicular cambium. Okay. Dedifferentiation means when a cell loses its functional property, a functional differentiation. That means a epidermal cell, cortical cell, parenchyma cell, collenchyma cell, any kind of cell becomes forgetful of its function and converts into a dividing cell. Dividing cell means meristematic cell. This is called a process of dedifferentiation. Okay. Now you can say thus a continuous ring of cambium is formed. Now you can say intrafascicular cambium plus interfascicular cambium together form cambium ring. Okay, you can say both intra and interfascicular cambium together form cambium ring. Okay. Now we have to study the activity of cambium ring. Cambium ring is formed. Now we will have to study the activity of cambium ring, which forms new wood. So now put the heading, second step, activity of cambium ring. Activity of cambium ring. So diagrams you have already seen. There is nothing great to describe that way. You will now say the cambium ring now becomes active. Earlier it was inactive. Earlier cambium was inactive. When it forms cambium ring, then only it becomes active. Otherwise it is not active. Okay. The cambium ring becomes active cambium ring becomes active and begins to cut off new cells and begins to cut off new cells. Okay. Both towards outer side and inner side. Outer side and inner side. It begins to cut off new cells. All right. Now we have to tell this here that the cells which will be formed outwards, they will convert into xylem, they will convert into phloem cells, and the cells which are going to cut inwards towards the center, okay, every cell will be pushed inwards, that will be converted into xylem cell, and the outer one, you understand, it is phloem. Now if you remember, I told you that xylem and phloem are complex tissues. So if they are complex tissues, it means it will be made up of many types of cells. All types of cells will be cut by cambium. All types of cells will be cut by cambium. Now what are these types of cells? Xylem vessel, xylem tracheates, xylem parenchyma, xylem fibers. But vessels will be highest in number. Similarly in phloem, companion cells and sieve tubes will be highest in number, along with phloem fibers, phloem parenchyma. They will be formed. Okay. So all complex cells, tissues will be formed, but normally when we talk about it, we say only xylem, only companion cells, or sieve tubes. But that is not the case. Every cell is formed because it is a complex tissue. The tracheid will also be formed, but very, very less. Parenchyma cells, less. After a xylem vessel, the next cell which is formed is, in highest quantity, it is xylem parenchyma. So please write quickly. The cambium cell, this is a cambium cell. This is the inner side. This is the outer side. The cambium cell forms a new cell, and this new cell immediately converts into a phloem cell, like this. So this is a phloem cell. The cambium cell also forms towards the inner side a new cell which will almost immediately convert itself into a xylem vessel. Xylem. Wait a second. I will use a different color because it's getting erased. Xylem. So now please write. The cells cut off towards the pith, cut off towards the pith or inner side differentiate into secondary xylem. The cells cut off towards the pith or inner side differentiate into secondary xylem. Alright. And the cells which will be cut off towards the outer side, cortex side, epidermis side, they will be differentiated into the phloem cells, secondary phloem. Let's complete this in a single sentence, no need to write two separate segments. And cells cut off towards the outer side differentiate into secondary phloem. Okay. Now you must write the cambium is more active towards the inner side. The cambium is more active towards the inner side. Cambium is more active towards the inner side. Towards the inner side. So more secondary xylem is formed compared to secondary phloem. More secondary xylem is formed compared to secondary phloem. All right. Now, because of continuous activity of forming xylem, primary and secondary phloem will always get crushed. Always get crushed, and new phloem has to be formed continuously. Due to continuous activity, activity of cambium, both primary and secondary phloem are crushed. Both of them are crushed. All right. Okay. So, how many people of you have eaten dalchini? Dalchini, everybody remembers? It's a ingredient of garam masala or Maggi masala, whatever you want to call it. Yeah, so it's cinnamon. Cinnamon is present in so many substances, and cinnamon is the outer bark containing phloem, primary and secondary phloem. Okay, cinnamon is the outer bark of the tree. So now we have to define another term called bark. So how many people of you understand what is bark? How many people out of you understand what is bark? If we, other than cinnamon, do you eat any other bark or consume or use any other bark other than cinnamon? Any other barks that you know of? Nobody? Okay. So how many people out of you, because northeast people have very good and very rich monasteries, Buddhist monasteries. In fact, northeast is the only part, northeast and south India are the only parts of India which were not raided by invaders. Because of the fierce determination of the local people, these were never invaded. Okay, I know the history of the northeast. So we have undisturbed, untouched, undestroyed temples and monasteries in northeast, and these have many beautiful scriptures. Yeah, everybody knows, right? And these scriptures are written on the bark of Betula palm tree. There is a bark of tree called Betula palm, and the very thousands of years old, hundreds of years old scriptures, they are basically written on either animal skin or in most cases in the on the bark of Betula palm tree. Okay, and that is basically the primary phloem and secondary phloem along with the cortex, dried cortex. Okay, so anybody has seen a real scripture in person? It's very difficult to see it because they have to be kept preserved, so not everybody is allowed to see it, but still you can see fresh Betula palm new scriptures written on it. Have you seen it? Yes or no? Okay, somebody have seen it. Some people have seen it, somebody have not. So whenever you visit a Buddhist monastery, ask the monks there that, sir, we want to see some Betula palm scriptures. Can you show us? So they will definitely show it to you. It's a very enlightening experience because the atmosphere is so good, and it's really nice to hear the chanting and all that. So I really like that. I hope that you also like this kind of thing. All right. So let me continue. Both primary and secondary phloem are crushed due to continuous formation of okay, yeah, already have written that continuous formation of due to continuous activity of cambium. So it's enough in it. All right, so let me start the next thing. All right, however primary xylem remains intact. It is not destroyed easily near center. Central part remains more or less not destroyed. All right. Also, at some places, cambium also cuts parenchyma cells. Cambium also cuts parenchyma cells and because these have been formed at later stage, they cannot be called primary medullary rays because they have been formed from secondary origin, so they will be called secondary medullary rays. Cuts parenchyma cells forming a narrow band, which passes through secondary xylem and secondary phloem. Secondary xylem and secondary phloem. Secondary xylem and secondary phloem. in radial directions, in radial direction. So it will be like a radius like this. Okay, so it will be in the form of a radial pattern like this. Right? So because it's radial, so you will have to call it a ray. A ray means a linear arrangement. Okay. All right. So we will write this. These are called secondary medullary rays. These are called secondary medullary rays. These are called secondary medullary rays. Okay. All right. Now let's continue with spring wood and autumn wood. Let's put the heading. Spring wood. Okay. Spring wood, autumn wood, and annual rings. We have to cover this now. Spring wood, autumn wood, and annual rings. Okay. So I want you all of you people to look at your desks. Okay. So everybody is sitting on a beautiful wooden desk. Okay. So yeah, everybody can look at your desks, right? Everybody is sitting on a very fine specimen of, I think it is Tectona grandis wood. I think the wood that is used in the making the furniture of your classroom, it's probably Tectona grandis or teak wood. I'm not very sure, but I think it is, because looking at the texture of the wooden table, it's teak wood. And you can see that there on that wood, that wooden table that you are sitting on, some people are using a plywood, I think. All right. So on that you can see some dark and light patterns. Please take a look at your desk closely. You can see some dark and light wood, right? And you can see some lines over there. Everybody can see some. So everybody can see some dark and light patterns. Okay, this is one thing. Another thing is you must take a look at the lines. Okay, the wood that you are sitting on, it is an oblique section of the tree it was cut from. It is an oblique section. Transverse section is like this. Vertical section is like this. The wood that you are using, it's an oblique section because we want long pieces of wood. And long pieces of wood have this beautiful ability to show wood in very different patterns. If you cut a transverse section, we will get only concentric ring pattern. If we cut a longitudinal section, then we will get a vertical lines. Okay, straight lines, no concentric rings. But if we cut a oblique section, we will get a mixed pattern. It between circular and linear. That is what the wood is all about on the furniture wood. Because it looks beautiful, so always we cut not transverse section, not longitudinal section, but oblique sections. And we also get longer pieces of wood. On this wood, if you see carefully, you can see some light colored regions and some dark colored regions. Okay, the furniture wood. So why does this happen? The reason is when there is unfavorable condition for the plant. Suppose it is winter season. There is no photosynthesis. There is no food coming for the plant. It has to use the stored food in the root. Under this condition, the plant will not be able to make very, very large vessels. It will make vessels. These vessels are larger than protoxylem, but it cannot make them very large because requires a lot of resources, because it requires a lot of resources. So what does the plant do? Plant makes xylem, but the xylem is very small in diameter. The xylem is very small in diameter, like this. So it is making it. It can be 2 layer, 3 layer, 4 layer, depends upon how long the unfavorable season is, right? Like this. And when the favorable season will come, now the vessels that are formed will be larger in diameter, like this, larger in diameter. So if you take a look at the table with the help of a low power microscope, you will see this kind of arrangement: larger vessels and smaller vessels. Now if you look at them from a great distance, because these vessels are very small also, then you will see it from large distance. The small vessel small diameter vessels look like a dark line, and the large diameter vessels look like a lighter colored line. Okay, so one dark and one light band, they are formed in one unfavorable season and one favorable season. That is what a year is all about. Every year there is a favorable season, a spring season, there is an unfavorable season, which is the autumn season, the leaf fall season. So because of this alternation of seasons, dark and light wood is formed, which is called spring wood and autumn wood, and these together form one annual ring. Why annual ring? Because these are formed in one year. Okay, so please write this now. The cambium activity, okay, the cambium activity is dependent upon the control of external physiological conditions, physiological and environmental factors. So if plant is facing stress, it will show in the wood. Okay. All right. So where did this, now there is another question. Seasonal activity varies from latitude to latitude. Seasonal activity varies from latitude to latitude. Why? Because in tropical region there is rain every day. It's raining every day. So in that condition, this condition will not be observed. In that climate, this condition will not be observed, because every day there is rainfall, every day there is favorable condition or uniform condition. So whenever plants are growing in a uniform condition, this annual ring will not show. Okay, so when will it show? Annual rings are most clearly visible in those areas which are having very sharp variation in climate. So in those areas in the northeast which are permanently covered with snow, okay, in the winters, and in summer the snow melts and there is favorable season, the spring is very well defined. In those areas the annual rings will be very, very sharp. The wood that you are sitting on is not actually very, very sharp, but in those areas which are in the hill station areas, in those areas there the wood will be very, very distinctive annual rings. There is a question that has been asked in your NEET examination. Out of 4 places you have to choose a place. If you plant a tree there, you will get very clear annual rings. Okay, so you have to, there are 4 cities: Delhi, Kolkata, Chennai, Shimla. If a tree is growing at one of these or all of these 4 places, which tree will show very clear distinct annual rings? My question to you is, out of these 4 places, out of the following places, yes, exactly, Shillong, you got it right. At which place will a tree show? Okay, Balaji, you answered it right. Okay, I'll remember that. Show clear annual rings. Or well defined annual rings. Delhi, the place where I am right now, Shimla, Kolkata, Chennai or Mumbai. Let's take Mumbai. Look, Delhi has some climate extremes, but not like Shimla. Kolkata and Mumbai, these are basically coastal cities, almost coastal cities, not exactly coastal, but they are almost coastal cities. I can also include Chennai, 5th option, Chennai. So these are close to the sea. So these cities experience uniform temperature year around. So there is no clear cut distinction between favorable and unfavorable. Every season is favorable, or every season is less than favorable, slightly unfavorable. But there is uniformity in season. So if there is uniformity in season, then there will be no annual rings. If there is non-uniformity, then only there will be annual rings. This is the question why I am asking. Okay. Right, let's complete it quickly. The cambium. Now let's come back. The cambium producing new xylem in unfavorable conditions, unfavorable or autumn season, or autumn season will show lesser diameter vessels. However, in favorable conditions, however, in favorable conditions, new xylem will be having larger diameter vessels. Larger diameter vessels. So together, combine them together, lesser diameter or smaller diameter plus larger diameter vessels, and together they form a annual ring. Therefore, due to two kinds of wood, one light and one dark. This is darker, one darker and one lighter. Appearing in alternate arrangement, appearing in alternate, that means dark will also always follow light followed by dark, always alternate, never continuous, appearing in alternate fashion, appearing in alternate fashion, constitutes one annual ring. Why one annual ring? Formed in 1 year. Because it is formed in 1 year, so we call it one annual ring. Okay. So if we count any annual rings in the tree, we can determine its age. So now next point you will write, age of a tree can be determined with the help of counting annual rings. Age of a tree can be determined by counting number of annual rings. By counting number of annual rings. Clear? Now, an apparatus is used to count the annual rings and it is called a dendrochronometer. An apparatus used to count annual rings is called dendrochronometer. Dendrochronometer. The science of counting annual rings or determining age of a tree is called dendrochronology. Apparatus is called chronometer. Meter is a general term. Meter is a general term. Measurement, thermometer, okay, respirometer, osmometer. Meter is a general term used for apparatus used for measuring a quantity. Okay. And logy, biology, zoology. Okay. So these are the terms used for a branch of science concerned with the study. Dendrochronometer, science of determining age of tree is called dendrochronology. Now I'll explain what dendrochronology and dendrochronometer is. Okay, and one more thing, darker wood, please make a statement. This darker wood is called autumn wood. Autumn wood, and lighter wood is called spring wood. Please make this change. Sorry, an addition, sorry, not a change. Darker wood is called autumn wood, lighter wood is called spring wood. Okay. So darker wood, autumn wood, spring wood. Now let me explain to you what dendrochronometer is. Look, right now I can only tell you, like, just a second. For example, suppose I have a very old tree. It's supposed to be 100 years old or more, like the great banyan tree is about 300 to 400 years old. Okay. So how do we determine the age of tree without cutting the tree? Can you give me an estimate? If you want to count the annual rings, normally you will assume that you will have to cut the whole tree. But is there any technique by which you cannot cut the whole tree and still you can count the number of annual rings? Is it possible? Is it possible by not cutting the whole tree? Just try. The answer is very easy. It's really easy. I don't want you to cut the whole tree. Suppose there is a giant redwood tree, and suppose you don't want to cut it down. There is a very old angiosperm tree also. Gymnosperm we do not count annual rings because they have a different pattern, but angiosperms we always count annual rings. So there is one tree, it is estimated to be about 700 years old. So it must have 700 annual rings. So will you cut the whole tree just to count the number of annual rings? That is not good, right? So what do we do? How can we solve this problem? Anybody? Take a guess. You don't have to cut the whole tree. There is a technique. How can you do it? That apparatus is called dendrochronometer. Now I'll explain to you what dendrochronometer does. Look, if I don't want to cut the whole tree, there is a way. There is a way. I only have to take a small section, very, very thin section. Even this is thick. I want to cut a very, very small section like this. Very, very small section. Not even a pizza slice. Very, very small section. An apparatus is called dendrochronometer. It's like a corkscrew. I push it deeper and deeper and deeper, okay, until and unless it's the last limit. So I push it as much as possible, okay. So I push it maximum depth, okay, and when I reach the maximum depth, that means the center, then I stop, okay, and then I take it out, okay, and this whatever part has been cut by the corkscrew, there is a blade outside. It keeps on cutting. It keeps on cutting. And now I have a small, almost circular section up till the middle of the tree. I will take this section out and now I will count it. The number of annual rings. I just need a very small section. I don't need to cut the whole tree. What is the use of cutting the whole tree? The tree will also stop growing. You will stop getting people who visit that tree. Okay, there is no use. And right now there is no X-ray machine also that we can use. The simplest method is to take a apparatus called this dendrochronometer. It works like a corkscrew. I push it deeper and deeper. And finally, when I reach the center, I take it out. There will be a hole in the tree. Okay, but the tree will still survive. Okay, there will be a hole in the tree. And the tree will slowly heal itself, but the tree will survive. Then I very carefully use a microscope and count the number of annual rings. Okay, that will give me the approximate age of the tree. Normally it is quite accurate, so that will give me the age of the tree, that how many years old it is. This is what is dendrochronometer is about. And this science is called dendrochronology. Many fossils, we do not use very large fossils. Unless and until they have a good pattern of secondary growth. So if they have a good pattern of secondary growth, then we use dendrochronometer. Otherwise we do not try to harm the fossil, and then we count the annual rings. So just to tell you, this is the science behind counting annual rings. Now we have another subtopic in this category. It is called heartwood and sapwood. Heartwood and sapwood. Heartwood and sapwood. So now look at the table that is in front of you. Look at the table and the desks, the chairs or the long stools that are there. You can see some dark brown spots. These are very clearly visible. I can see from the camera here. Okay. So these are very clearly visible on your desk. Dark brown colored wood and light colored wood. Okay. I am not talking about the very fine lines. I am talking about the dark colored circular patterns. Okay. This is the heartwood. This is the heartwood. When I talk about a tree, when I take a look at the old tree, near the center there is a brown colored, dark colored portion. It is called the heartwood. It is called the heartwood. This part is called the sapwood. This is the outer lighter colored portion. So I told you yesterday that if you are going to buy a piece of sandalwood, try to pick a piece that is darker in color and has more black or brown colored portion in the middle of it or anywhere. That will have more scented quality because that is older wood and that will have more essential oil, more resin, and it is more useful. Okay. So please write now. In old trees, the greater part of secondary xylem is dark brown. Due to deposition of organic compounds. Due to deposition of organic compounds like tannins, resins, oils, gums, aromatic substances, and essential oils in central or innermost part of the stem. Now, what does these substances do? They make the wood change its property. Now this wood is becoming termite resistant, pest resistant, fungi resistant, maybe even waterproof. Okay, and it might acquire a medicinal value in some plants. So what does this do? These substances make it hard durable, and resistant to the attacks of microorganisms and insects. Microorganisms and insects. Okay. It makes it resistant to the attacks of microorganisms and insects. All right. This region, what does this region comprise of? So the thing is, try to understand it like this. I am having a central part, it is having parenchyma cells, it is having xylem cells. Now I am filling tannins, resins, oils, gums, lot of things in the central portion. The central portion is all filled with these things. So will these cells remain living? No, they will all die. But because these substances are being constantly deposited, so these will ultimately be converted into a very hard form. So these will be ultimately converted into a very hard form, and this hard core, it is called the heartwood. The darker colored portion that is visible on your desks, it is the heartwood. So please write it quickly. These substances make it hard. This region comprises of dead cells. Basically xylem vessel elements plus parenchyma. With highly lignified cell walls called heartwood. This means primary wall, secondary wall, tertiary cell wall will be present. Even tertiary cell wall made up of high amount of lignin. Highly lignified cell walls or cells, okay, just a second, walls not cells, highly lignified walls called heartwood. What is the function of heartwood? Function of heartwood, it only provides mechanical support. Okay, it provides mechanical support to the stem. Okay, the outer one more thing, heartwood does not contain water and minerals. Heartwood is dead, and even though it is dead, it is fully blocked. It does not conduct water and minerals. It is blocked. It is blocked with stored substances. It does not take part in water and mineral conduction. It does not take part in water and mineral conduction. Okay, it does not take part in water and mineral conduction. Now let's finish the sapwood and secondary growth in dicot stem. In the due to cambium will be finished, then we will finish cork cambium quickly. Sapwood. What is sapwood? The light colored outer portion is called sapwood. The lighter colored outer portion, outer or peripheral region of secondary xylem is called sapwood. It is involved in water and mineral conduction. It takes part in water and mineral conduction. It is having living cells also. Water and mineral conduction. With this, finally, secondary growth in dicot stem is completed. Half portion is completed. Now, very easy portion remains, formation of cork cambium. Okay. Formation of cork cambium. So, please finish this quickly. And we will move on. Okay. So, if you want to see hardwood and sapwood, it is visible on your desks, very clearly visible, very sharp patterns. Okay. All right. So, let us continue. Please put the heading formation of cork cambium. Formation of cork and cork cambium. Formation of cork and cork cambium. Now, the thing is, due to continuous secondary growth, due to continuous increase in thickness, please write, due to continuous increase in thickness of the stem, continuous increase in thickness of the stem, the outer cortical and epidermal layers, the outer cortical and epidermal layers get broken and need to be repaired or replaced. If you do not repair it, it will be broken and pathogens will attack. repaired or replaced. So how do we repair it? The cortex cells will undergo dedifferentiation and form new cells called cork cambium cells. This cork cambium is also known phallogen. Phallogen forms new cork cells on the outside, and on the inside it forms new cortical cells called secondary cortex. Why we call it secondary cortex? Because primary cortex was formed initially. Now it cannot be formed again. So how do we form it? With the help of secondary meristem called cork cambium. So because it is formed due to secondary meristematic activity, we call it secondary cortex. So please write this quickly now. Therefore, some cells of cortex undergo dedifferentiation, to form cork cambium. So cork cambium is formed from primary permanent tissue. Primary permanent tissue gives rise to secondary meristematic tissue. So this is dedifferentiation. Cortex has parenchyma cells. Okay, cortex is primary permanent tissue. It gets process of dedifferentiation. It undergoes process of dedifferentiation and converts into cork cambium. Cork cambium is example of secondary meristematic tissue. Please finish quickly. Okay. So cork, how many people have used cork in any part in your life? Have you seen, touched or used cork? Cork is a dark colored substance, brown or black. It's used in bottles. So how many people of you have at some point in life opened a champagne bottle or many other bottles? But locally made wine bottles also might have, you might have seen a cork, the popping sound. Okay, you might have seen F1 races, football matches where people open champagne bottle with a pop sound. So that pop sound is when cork is suddenly removed. Okay, just raise your hands if you have seen or used cork. Yes, okay. Yeah, some people have. Okay, thank you. Thanks. I am happy some people know. So those who know, they can also show their friends, like this is cork. Okay, so it makes a popping sound and it's very nice to watch. I don't drink, but I like the popping sound. Okay, so this is about it. Cork cambium. Okay, now let's write about cork. Cork cambium forms new cells having deposits of Subrin is another name for cork. Because of high subrin deposit, the cells formed on the outside of cork cambium become dead called phellem cells, phellem or cork cells. Okay. On the inside, okay, one more thing, cork is a waterproof substance. Cork is a waterproof substance. Cork is a waterproof substance. Waterproof fatty substance. And helps in repairing the broken outer layer. All right. So it's a fatty substance. So you can say it's a cream for the plant for healing its cracks. So if you have some cracks on your skin, you apply some moisturizer, Pond's or Lakme, or I don't know. So many brands are there. Nivea maybe. Okay. So for the plants, they use cork. They also have dehydration problem and skin cracking problem. So they use cork. And some plants produce excessive amount of cork. These are used commercially. Example is Quercus suber. Some plants produce, cork is formed in every tree. Neem tree, eucalyptus tree, every tree forms cork, but some trees form large quantities of cork, so which can be commercially used, economically useful. Some plants produce large quantities of cork, so used commercially. Example, Quercus suber. It is also called oak tree. Normally, wine is made in oak barrels because they are waterproof and alcohol proof as well. So they are used to make seasoned wine, vintage wine, 100 years, 200 years, 12 years. Okay, so it is made by maturing the wine in oak barrels. So that is how oak tree is used. Cork is used in this way also, used to make waterproof wood also. So that wood taste goes into the wine, and the more taste of wood goes into the wine, the more expensive it is. Cork cambium or phalogen or phallogen also forms cells for repairing cortex, cells for filling the cortex called secondary cortex. These cells are parenchymatous. These cells are parenchymatous. Okay. Now the secondary cortex, this is called secondary cortex. Secondary cortex is also called phalloderm. Phalloderm. Okay. Now, because you are in droppers, you might have seen one very good question. Bark is made up of. Sir, it's time. Okay, you want to remind me? That is time. Okay, we are having a last part called secondary growth in roots. I was trying to finish it, but because you won't let me. Okay, all right. So I will give you a homework. Try to find out bark, layers of bark. When you go home, try to find out bark has how many layers. Okay, in the next class I will tell you this. So this is a question. I want the names of the layers. Names of layers. Okay, so you will have to tell me the names of layers, and I will discuss this in the next class. Okay, so I will also make a PPT for you for the secondary growth portion. I hope you find that interesting. So that will include a lot of beautiful scripture paintings and the Jataka paintings regarding secondary growth. There is a lot of literature and a lot of beautiful stem cuttings and all that. So I'll send you that. Okay. So just give me time till the next class, and I'll send you that. You will find that very interesting. Okay. So thank you, dear students. Thank you for your time, and have a great day. Enjoy your lunch. Thank you.